Hi, let's talk about computational fluid dynamics. In this video, I'll talk about CFD, the basics, how it works, the working algorithm, all the steps involved, particularly one step, the discretization. And again, in that, one small discretization method, which is the finite difference method. By using it, we'll solve a couple of problems, and that is how this video is going to go. I'll not talk about coding or any other aspects. We'll leave it for some other day. Alright, so let's get to it then. Okay, now if we talk about engineering or say in general problem solving, so we have more or less, three different approaches. First is analytical, right? Second would be experimental, and third is numerical. Obviously, there are different ways, but broadly we can categorize them into these three categories. So in the analytical approach, what happens is that we solve or get exact mathematical solution. So we solve equations by using an approach which leads us to the exact solution. So there's no assumption, there are no blatant errors, the exact solution. That's it. And same in experimental, what we do is we take direct physical measurements. Ergo, we study the exact physics. Again, no adulteration involved. And in numerical method, unlike both these methods, we do make assumptions, and we obtain approximate computational solution. All right. So this is the primary difference between the three methods. That in analytical solution, we get the exact solution. In the experimental approach, we make direct physical measurements, we build experimental setups, we try to capture the physics as it is. And in numerical method or approach, we have an approximate solution. We make some assumptions, and ergo, or therefore, rather, my bad, we get some solution, but which is approximate. We'll talk about it. So here we can only study simple geometries and linear problems due to the fact that we are going to solve mathematical equations directly. So we are limited to simple geometries and linear problems. When we enter into a complex physics, or when we talk about some complex physics, there the mathematical equation accordingly gets very complex. And by using an analytical method, getting the exact solution becomes very challenging. You can look up the $1 million problem of Navier-Stokes equation. If you get the exact solution of Navier-Stokes equation, you receive $1 million. And that's how impossible it is to get the exact solution of such highly nonlinear cases. What about experiments? Now since we are talking about experiments, we are going to build experimental setup. Here, the limitation or the applicability depends on the real world conditions. So what kind of a situation are we looking at, and obviously what validation? In the sense, let's see, uh, we are looking at an example or case where, say, there's something medical in nature, or which involves a lot of economical aspect, or even, say, security aspect. For instance, if I want to test physically what happens if an aircraft crashes into a village, that what is the maximum that is the area that is hit, and how many people may die, or how much of loss it may happen in terms of the debris, how far they may reach, what is the area of impact. I cannot do this on a real life situation. Obviously, I can simulate this in the sense that I can do this somewhere remotely and check, but it's going to cost a lot of money. All right, what if, suppose, I want to simulate the irrigant flow in a root canal treatment? So I call you and ask for your healthy tooth, so that I can do all these experiments on you, different type of needles maybe for irrigation, or maybe I have come up with an artificial heart. I have to test it on someone, so I cannot test it on a healthy human being, or even if they are on some sickness. But then it's ethically and also morally and also realistically very challenging. So experimental approach has its own limitation. As I said, it all depends on the real world conditions and validation. So how far, how feasible it is, it all depends on that. So let's talk about numerical method now. So numerical method, it is a saying in Hindi, "Jahana pahunche Ravi, wahan pahunche Kavi." That means where these analytical and experimental approach fail, or maybe cannot give us answers, numerical method, we can rely on numerical method. In general, we can rely on numerical method, but specifically in these cases, we can rely on numerical method especially. So the two examples that I gave, I can simulate that by using the numerical method, by using computational simulations. So here, if we talk about applicability, yes, we can work on complex geometries, complex realities, and we can solve the Navier-Stokes equation that you were talking about by using this approach. Yes, it works just fine. So let us talk about the cost. Now see, cost-wise, analytical solution very low, literally, because we're going to solve it. We're going to directly, get the solution of governing equations. Mostly, very less computing power is required. So analytical solution, the computational or the running cost, it's very low, right? What about experiments? It is, or would be, relatively high in comparison to both these methods, for the very simple reason, you have to purchase things, you have to manufacture things, you have to put them together, then you need people to do this, you need to pay those people, and the time aspect. So yes, if you talk about cost and time both, the time also would be relatively low, for the very simple reason that we would be solving equations, so it's relatively low here. What about experimental setup? Very high, relatively, again relatively high, very high. As I said, you have to assemble the setup, you have to get it running, you have to calibrate it, you have to validate, and all those things. Yes, of course. So no, experimental setup very high, time. What about numerical method then? Now here, it will fall in between the analytical and experimental method, meaning here the cost would be more than analytical and lesser than experimental. So I would write moderate. Same, moderate. Why do I say this? For a very simple reason. Say, for instance, I have to simulate flood in a city. So here I need to model the buildings, I need to create the mesh, I need to simulate the flow. Depending on what kind of computing power do I have, it will take a certain time. Then I have to post-process the results. I have left out the validation and verification procedure that also needs to be done. Then there is gradient dependence test and all those things. So it will take some time. So it's more than analytical, but surely less than experimental. Obviously, you can go crazy and run a very long simulation, but I'm giving you a general scenario. What about cost? The primary cost in numerical method or the computational simulations would be the computing power. So your PC, your server, your workstation, how crazy system you have, it all depends on that what is the price, right? So this was about time and cost. What else? What do we, or what can we include in it? Yeah, parametric studies. So here, can we do parametric studies in the analytical method? Yes, we can do, but the scope would be limited. The scope would be limited because you need to, you have a governing equation, but it has a limited scope. So there, you may have to broaden, or new derivations may be required to be done. So yeah, parametric studies, limited scope. What about experimental? Again, this is going to be really expensive. Too much money would be required here, because and what does this mean, or in real life terms? Say, for instance, I want to simulate fluid flow across a simple cylinder. I'm giving you a very simple example. So we've got a cylinder and we are simulating flow around it. Beautiful. So for instance, I've developed an experimental setup for this, and now I want to study flow across maybe a square cylinder, a diamond cylinder, a triangular cylinder. I want to change the shape. Like this, I want to do a lot of shapes. So here, I will have to, amend the setup for every shape. Going to take time. There will be money involved. And I have given you a very simple example. You make it, or you apply to a very complex problem, more money. What about numerical method? Very easy. Why? It is all about changing numbers. You have already written a code, it's running all perfectly fine. You just change numbers. You can run thousands, lakhs of simulation. No one is stopping you. And it doesn't cost much. What about accuracy? Analytical approach will have the highest accuracy, right? Experimental approach, again, will have very high accuracy. But then there are limitations. What are those limitations? In analytical method, again, we get the exact solution, again, within assumptions. What assumptions you're making within that. But we do not make crazy assumptions in the exact method or in the analytical method. So you get the exact solution. What about experimental? Again, here, within the reading restrictions, right, you will get the results. And what do I mean by that? So, or the precision. See, experimental approach is all about measurements. And for measurements, we do need devices. And how accurate are those devices? Your results will depend, or the accuracy will depend on that. Right? So your accuracy depends on the measurement capacity. So in the experimental method, you get the exact results, but with this restriction of precision. What about numerical method? Now here is the thing. In numerical method, the accuracy, it is completely subjective and subjective to a lot of things. One thing particularly, which is discretization, which we are going to talk about in this video. So, I always say that as a CFD engineer, your results are as good as you are. The kind of assumptions you make, the kind of discretization decisions you make, the kind of schemes, the kind of solvers, the kind of mesh that you create, it's very, very complex. The variables are like too much, and hence it depends on the person behind the keyboard in this case, right? So that's that. We have talked about accuracy. Let us talk about what else can we talk about? We have talked about this. Yes, let us talk about some examples, right? Let us talk about some examples. Say for instance, if we talk about an analytical solution, we will be looking at maybe one-dimensional conduction. And if I write an equation, right, so one-dimensional conduction, so I would write something like this. In this case, gamma would be alpha and this. So here the exact solution is possible. How? You integrate this twice. And you would get the solution. What would be the solution? Simply this. It is as simple as that. What about the experimental approach? What can be the examples, or what are the popular examples in at least as far as fluid dynamics is involved? So if you have ever come across a wind tunnel, we often use wind tunnels, or maybe I can give you example of crash tests. We conduct on car. Some good examples of our experimental method. What about numerical method? So numerical method would be, obviously we have CFD, then there is finite element analysis, even weather prediction uses numerical method. Right. So these are some examples. So to summarize, we have compared the three problem solving approaches, which is the analytical method, the experimental method, and the numerical method. Right. We talked about their basic working principle, that in analytical solution we solve the governing equations for exact solution, right? So we have talked about the approach. So here we solve for the exact solution. In experimental method, we make direct physical measurements. In numerical method, we make some assumptions and we derive the solution. So it's an approximate solution. Then we have talked about the kind of complexity you can cover, right? In an analytical method, the complexity is very limited. You will study simple problems. In experimental method, the complexity is limited by the realistic conditions, in the sense that how far you can go, or which say setup or physical conditions you can reproduce. It all depends on that. So that's the experimental approach. And in numerical approach, the complexity, it all depends on the availability of the governing equations, the availability of the physics, but it is much more flexible in comparison when you make a comparison to analytical or experimental methods. What about the numerical method? The numerical method example for this application I have given you, say for instance in biomedical cases where the experimental approach cannot reach and analytical approach totally fails, numerical approach can work out. I have given you the example of the crash, and I had given you the example of root canal treatment. You just take any biomedical example, it fits perfectly fine. Then we talked about cost and time required. So as far as the cost is concerned, analytical approach is the cheapest, experimental approach is the costliest, and numerical approach just falls in between. We talked about the time. Likewise, analytical approach is the cheapest, numerical approach falls in between, and experimental approach is the costliest. We talked about accuracy. So here, accuracy wise, I gave you that how analytical and experimental methods are both very accurate. Numerical method is not so accurate, and in experimental method the accuracy will be limited to the kind of a measurement devices you have, and analytical method the accuracy would be depend on the kind of equations that are available to us and the approach that is available to us, but more or less we get the exact solution. So that was about cost and time and accuracy. We also talked about parameterization, that how easy or difficult it is to do this parameterization, or parameterize I would rather write. So in the case of analytical approach, doing parameterization is relatively difficult in the sense, or rather limited I would say, because it all depends on whether derivations are required or not required, and in an experimental approach obviously it's very tedious. In numerical method on the other hand, parameterization is very easy because it is all about changing numbers, editing your code, and you have the solution. So nothing, not too much difficulty in that area. So that is how they fare against one another. Now moving ahead, we'll talk more about numerical method. We'll talk specifically about computational fluid dynamics, and we will talk how it works. We have seen a fair comparison between the three methods. So the question arises that when do we use the numerical method? Right. So when do we use the numerical method? The first point here would be that when the analytical solutions do not exist, and or they are impractical, then we would use numerical method, right? Or the geometry is very complex. The geometry is very complex. There we would use numerical method. We may also have the cases where we have non-linear equations and where we have variable material properties. In analytical approach, obviously varying this is tedious because for that new derivations would be required. In experimental approach, again, some properties or some material making them will take additional time. So there it's not that easy to test a lot of materials. On the other hand, in numerical method, again, it's all about changing numbers. So yes, in fact, I can go crazy and do a lot or study a lot of different material property combinations. Also in numerical method, we will use particularly this tool when we are looking at complex boundary conditions. So some like very complex phenomena is happening and we want to study its influence on our system, on our domain, then yes, we would rely on numerical method. And the last point that I would like to make is when, and this is very important, when we are looking at multiphysics conditions. So multiphysics conditions or multiphysics problems. Let me write multiphysics problems. We would particularly use numerical method in this case. What does multiphysics mean? Meaning, say for instance, we have a rod, and on that rod, we are looking at a situation where it is fixed at the other end, a load is being applied at the other end, and also maybe here there is a heating source. Right, there's a heating source, so heat is also being applied here. So you would see the expansion in the rod, the deflection in the rod, and maybe there is some situation where there is a time varying load here, and maybe there is an acoustic source here. So these kind of situation where a lot of different physics exists simultaneously, we will move towards the numerical method for the ease of application relative to other method. Not that it is very easy, but relative to the other methods, yes, it is fairly easy to implement. Right? So to sum it up, we use numerical method for these conditions, right? And we would also then decide which specific method we have to use. It's not like CFD use in every method. Now, where and why CFD is used, let us talk about it. So CFD would be used specifically in cases where we are looking at flow or fluid flow problems, complex fluid flow problems. We'd be using CFD there, right? So let us talk about CFD and what does it do. So CFD is, I can say that it's a branch of fluid mechanics, and it uses numerical analysis and data structures to analyze and solve problems. All right, which involves, and this is important, fluid flows. So what equation do we solve in CFD? We solve the Navier Stokes equation. So let me briefly write here a variation of Navier Stokes equation, which is very easy to understand. So we have the continuity equation, which is dou rho by dou t plus the divergence of rho into u is equal to 0. If you remember the conservation principle, this is based on that. We make sure that all the forces are conserved and even the mass is conserved, so energy is conserved. The conservation principle basically in fluid mechanics, or rather in computational fluid dynamics, by using or by solving this equation, we make sure that all the entities that we are trying to solve are preserved, are conserved. Then we have the momentum equations. Now, why did I write equations? Because we solve it for all the directions that we are dealing with in the space. And here I would write rho d by dt u minus nabla p plus should have written viscosity mu nabla squared u bar, which is a Laplacian operator, and then maybe we have body force. Now here d by dt obviously stands for the total derivative, right? And again, after this, I may even write the energy equation or the mass transfer equation. It all depends on what additional fields you are solving. So if suppose there are additional activities that are happening apart from this, we may write it or represent it in this fashion. and maybe there is some heat generation. This is one of the many forms that the Navier-Stokes equation can take. This represents more or less a general, laminar flow situation where, we are looking at a very simplistic representation of Navier-Stokes equation. So we will keep on modifying this equation depending on our purpose. Say for instance, there is no body force. We remove this term. Right? Say for instance, there is no diffusion. We remove this term. Say for instance, I don't want to model the energy at all. Remove this equation. I want to model, magnetic field. I add another equation. Say mass transfer, I add another equation. So depending on the situation, depending on the physics that is involved, we will keep on changing this equation, which we refer to as the governing equation. Okay, the equation that governs your physics. All right. Let us move to now the general flow of CFD. That what is the common algorithm? The first step in this process is problem definition. This is very important, right? Because in this step, we will also talk about assumptions, right? What does this mean? Say, for instance, you are trying to simulate a situation of physics, right? Maybe for the sake of simplicity, consider flow across a blur body. So I want to simulate flow across a circular cylinder. Now here, how I define the problem? How do I define the problem? So I will ask myself, for simulating this, what are the things that are required? Again, the physics is very simple. We are going to simulate only the flow. So if that is the situation, what are the things that you may require for writing the code? So first thing is that understanding of what kind of a fluid that we are dealing with. So suppose it is water. You write down the properties of water. Its kinematic viscosity. It's an incompressible case, so density doesn't matter here. In the code that we write, you will look up. You will study it later on. So that's far as far as the material properties. That is what we need. What else we need? The velocity. So we'll define the Reynolds number, and based on that, we'll calculate the velocity. So that is what we need. Apart from that, whether it is a 2D problem, whether it is a 3D problem, whether we are going to do it steady state or unsteady state, all these kind of questions you ask, and depending on that, you define your problem. So suppose it's 2D, what assumptions do you make? You make that the cylinder is very long in the third dimension. It's so long that we'll ignore the third dimension altogether and we'll focus only on the 2 dimensions. So these kind of assumptions you make. Say for instance, we are talking about the material properties. We assume that it's uniform everywhere, right? These kind of assumptions we make, and that is how we'll define the problem. So once we have defined the problem and we have also included all assumptions and everything, then we are ready for the next step, and which is to draw the geometry, right? So we'll create the geometry. Now you use any CAD software for this, right? In this step, CAD will be involved. So we'll draw the problem and then we will discretize it. We'll discretize it. Or let me not confuse you. Let us just use the word mesh. We'll generate the mesh. We'll generate the mesh. So here, what we do is simply we split the space, the real space, into small pieces, and that process is called as discretization. That process is called as discretization. So it's like you slicing the entire domain into small pieces, and then we'll solve the equation in each piece and then put it all together. So that is the poetry of it. We, after the creation of geometry, discretize it, we'll generate the mesh. Discretize the space, so we'll create the mesh, we'll generate the mesh. And once this is done, we do all the physics setup. What does that mean? It means I write down the Gaussian equations, I see if there are any source terms or any additional equation to be involved. Then I'll define all the boundary conditions, right? Boundary condition. And then see at the beginning of the simulation, what are the things to be considered, which is the initial condition. And I do all this under one step, which is the physics setup. And once everything is done, as far as the physics is concerned, then I move to the next step, which is the numerical setup. Or let me write down numerical solution. So let me use the word setup. That should be more appropriate. Because in this step, what I do is I decide what kind of schemes, solvers, and all those things I'm going to use. When I'm going to write at what interval I'm going to write my case, and what format and all those things, the nitty-gritties of it. And once all this is decided, and let me put all this, this entire thing that we have discussed so far under one bracket, which is pre-processing. So once I am ready with this entire setup, I then go ahead for the next part, which is solution. So basically I run the code. The code runs, I get some results, and once I get those results, I perform the next step, which is called as the post-processing. Post-processing. And why is it required? Because see, when we run the code, numbers are read, numbers are generated, and we as human will not be able to appreciate those numbers if we just look at it. So we need to plot it. We need to convert it into XY plots, contour plots, and then we'll have to look at it and understand the physics that we try to reproduce. And this step is called as post-processing. So pre-processing involves setting everything up. Solution is like solving it, and post-processing is when you analyze the solution. It's just like cooking. So in pre-processing, the cooking would be it's like you take all the ingredients, set up it on the table, and then solution would be to cook it. And post-processing it, once it is cooked, you analyze it, you see if everything is done, you taste it, and then if everything is fine and if it is edible because you cooked it, you can eat it. So that is what it is. Now, let us look at one particular step which we mentioned, which is this step, where we did the discretization of space. Because see, all humans are different. They perceive reality differently. Likewise, someone may say that, okay, you know what? It would be best if we divide it simply in terms of nodes. Some may say, no, this is not the correct way. Let's split it into maybe control volumes. Some may say, elements. Some may even say, no, let us completely, disregard this step altogether. It's very slow. It's very complicated. Why not simply consider particles? Smooth particle hydrodynamics, meshless method. Someone may say, no, let us take lattices. In fact, let us forget the macro approach altogether. Let us take lattices, lattice Boltzmann method. So there are so many ways that you can go about this discretization thing. Innumerable ways. And some of them have become popular, tried and tested methods. And three of them are finite difference method, finite element method, and finite volume method. We'll talk about them. Right? So, what are we talking about now? We are talking about the process of discretization, its types. What are the types? The three popular: Brahma, Vishnu, Mahesh, finite difference, finite volume, and finite element method. Let us talk about it. Now, these are some popular questions whenever you interact, with any CFD expert, and if they are suppose interviewing you as a student, you are asked these questions. So this is one of the most staple question of the interviewers, that what is the difference between finite difference, finite element, and finite volume method. So let us talk about it. So finite difference method, right? Finite difference method is based on truncated Taylor series. Now here you will have to recall Taylor series. I will talk about it. And finite difference method is based on the approximates, derivatives of Taylor series. Finite element method, it is based on the variational formulation. And finite volume method is the broadly based on the conservation principle, where we make sure that the momentum, mass, energy, whatever we are modeling, are locally conserved, right? So it's more or less based on the conservation principle. If we talk about finite difference method, it is designed and it will work well on structured grids. What does that mean? So suppose if I have a domain, I split it and I solve in them. In fact, if we are talking about finite difference method, I solve at these points which are referred to as nodes. So that is what in finite difference method the structured grid means. Or in general, a structured grid is where you uniformly using the same shape with the different dimensions, but everything is very regular shaped kind of a thing. So that is structured grid, right? And finite difference method works perfectly fine on structured grid. Unstructured grid, very tedious to implement, but yes, on structured grid it works perfectly fine. Finite element method, again, it works perfectly with both structured and unstructured, and in fact it is very well known to handle complex geometries. Finite element method, remember, is popularly used for structural analysis for the same very reason. And if we talk about finite volume method, any mesh type, it works perfectly fine. No problem with finite volume method. Finite difference method, if we talk about the complexity of implementation, that is one more point which we can use to compare. It is very, very easy to implement. And exactly for this reason, anyone who is starting out in the world of CFD will learn finite difference method, because CFD as it is very complicated. And if you get stuck into the method itself, when will you simulate and solve the problem, and how will you get the motivation to move ahead? As it is, maths is disliked by many for the very reason that very less or very few people are able to relate it to reality, to the actual physics. And on the top of that, if you get into or stick into the complex procedure of solving the method itself, the results will not be attained. And then if you are not able to see those colors, those results, those attractive simulations, you'll not be able to motivate yourself to move ahead. And that's the reason why finite difference method is study. And when we are talking about finite difference method, is very, very easy to implement. Anyone with simple understanding of maths can learn and implement or write a finite difference code. It is that simple. What about FEM? What about FEM? Right. So FEM is easy to implementation. Yeah, it is fairly or relatively difficult in comparison to finite difference method for sure. And if we talk about finite volume method, right? Finite volume method is again, it's relatively difficult in comparison to finite difference method. Right. And what about the physics? Now see, both finite difference method and finite element method are based on mathematics, pure mathematics, right? So they are not inherently physical, meaning they don't take care of the conservation inherently. So for fluid simulations particularly, they are hence not a very popular choice. Now some people who use finite element method on a daily basis for fluid simulations may get offended, but I am talking about the broader public. There is one particular researcher, Mohsin Sheikhul Islami. He uses control finite element method, a combination of both finite element and finite volume method. So who am I to say? And because he is the top researcher, publishes almost hundreds of articles per year. So it is a method that works. That is what I'm trying to tell you in fluid simulation is concerned. But they both are not inherently physical. They're not inherently physical. What about finite volume method? Finite volume method, since it is based on the conservation principle, it is inherently physical and hence would be a preferred choice for fluid simulations. All right. Now, what about, and okay, we can make another point here. Now, since finite difference method is based or can be easily applied to structure grid, here complex geometries cannot be solved. Complex geometries cannot be solved, which is not the case for both finite difference and finite volume method. But for finite difference method, that is going to be a drawback, and we'll talk about it. All right. So I guess this is a sufficient comparison between three methods: finite difference, finite element, and finite volume. We'll now move ahead towards finite difference method because it's very easy to understand, very easy to implement. So let us talk about it a little more. So finite difference method, also known as FDM, right? And it's based on Taylor series, right? So suppose I write the forward Taylor series, I would write fx of h is equal to f of x, right? F of x plus h f dash x plus h square by 2 factorial f dash x plus the higher order terms. What about the backward Taylor series? How do we write that? So I can write fx minus h, f of x, my bad, the odd terms would be negative, so h f dash x plus h square by 2 factorial f double dash x and the higher order terms. Here minus the higher order terms. Right? Now, for now, let us look at a second order accurate solution and ignore the higher order terms. In essence, what is Taylor series? It's an approximation. So what we are trying to do here is that we are trying to guess the neighboring values based on the present value by using derivative terms, the slopes of the slopes, and we are trying to make some approximation, and hence inherently the finite difference method uses this because it's an approximation based method. So we are trying to use these differences, these finite differences, to simulate the fluid flow. Now let us look at both these equations. Right? Let us do a simple experiment. Add and subtract them. So we had f of x plus h minus f of x minus h is equal to, what do we have? And at this point, I would like to remind you, it would be best if you also have a notebook and a pen with you when you're watching this video, so that you can also write it and realize it. So we will be having here, because the first two terms, what were the first two terms? The first two terms were f of x. They both will get cancelled. What was the second term? The second term was h square by 2 factorial f double dash x. They will get cancelled in both the equations. What remains? What remains is this term. And I can therefore write f of x plus h minus f of x minus h divided by 2h. Beautiful. So now I have an equation for f double dash x and I have an equation for f dash x. So this gives me a liberty to readily convert any differential equation, second order differential equation, to an algebraic equation and then solve it. So let us understand what does this mean and what is this h and how can we use it. For that, let us take a very simple example which every CFD engineer or every person who studies numerical method, it is their first problem to study, which is the one-dimensional diffusion problem. So let us talk about it. One-dimensional steady state, and this is very important, steady state diffusion for solving problems. Right. So let me take a very simple case, which is one-dimensional steady-state diffusion, and let us apply the algorithm of CFD that we had learned earlier. So let me define the problem. First part was the problem definition. So the problem in hand is, I have maybe a rod. I have a rod, and that rod is heated at one end maybe 100 degrees Celsius and at the other end maybe 30 degrees Celsius. And it has uniform material properties. All right. And no additional phenomena. Only conduction. Based on this, I will then write its governing equation, which would be this. The diffusion coefficient. Now, since I assume the uniform material property, the diffusion coefficient that I had mentioned earlier goes out of the equation and goes and joins 0. So I will be left with this equation. ठीक है? I'll be left with this equation. And we have to solve this equation by using finite difference method. How do we do this? A couple of seconds ago, we have, in fact, derived already an equation for this. But let us not jump the steps. We have completed the first step. The first step was defining the problem. We have done that. We have also defined the assumptions. The second step was to model the geometry. We have done that. The third step was the mesh generation. So let us generate the mesh. I will split this domain into number of points. These points will be referred to as nodes. And I have discretized them into nodes, the domain. Why? What was the reason? Now, here, let us for a couple of seconds talk about discretization again. Now, see, this equation has an analytical solution. What is that analytical solution? You integrate it twice, you get an expression for temperature, you can plot it, and maybe you get a continuous temperature like this. So it's suppose 100, here 30, right? And or maybe let us represent it here. So this is 30, this is 100, this is the start of the rod, the end of the rod, and this is how you may get the distribution. Now here there are infinite number of points, and we have infinite temperature values between 100 and 30. Right? So, do we really need that information? Question number 1. And question number 2, what if we can't access that information? What if I can't solve this equation altogether? What do we do then? So what we do is we say that, okay, fair enough, I do not need to know the temperature values at all these points to reproduce this curve. I can even reproduce this curve by knowing finite number of points. Notice the word finite. And I can make assumption of the pieces in between. Obviously, in finite difference method, we don't do that. We don't assume what's happening in between. We are more or less focused only on the node, and what we solve, we mention, and end of the story, post-processing, whatever happens, happens. But other methods do rely on these, and we'll talk about it maybe in the next videos. But for now, this is the principle. The principle is, you have a domain, you discretize it in finite number of nodes. Question: how do you decide how many nodes? Answer: depends on accuracy and computing power. If very high accuracy is involved, you need a very fine nodes, and if you make this a mesh into very, very fine mesh, that means what? You are increasing the number of nodes. What does that mean? You are moving towards continuity, away from discretization, more accurate solution. But that means more computing power. If you don't have the computing power, now here you will have to do a balancing act, and you will have to select the number of nodes accordingly. Simple. All right. Now, with that information, we have completed the step of mesh generation as well. Now, let us do the physical setup. What can be the physical setup here? We can define the material properties. Here, luckily, we don't need to perform that steps. Let us move ahead. What was the next step? Numerical setup. What is the numerical setup? Let us write the governing equation. We have written the governing equation. What else do we need? We need now the discretization equation. We need now the discretization equation. So let us write the discretization equation. How do we do that? How do we do that? We have just done it a couple of seconds ago. What should be the discretization equation for this? Pause the video, think about it. Do not scroll or do not go a couple of seconds again in the video. Think about it. What should be the equation? So let me divide this domain into maybe these number of points for now to understand. This is the boundary node. Maybe I will write TB1 and TB2. We know the values of TB1 and TB2. Now it's our task to find out these fire temperature values. Right. How do we write? So let me draw a template mesh. Let me call this my present node. In that case, this will be the future node and this will be the earlier node. Or when I write future, I should mention that this is the node on the right. This isn't the node on the left. We have not yet talked about time, only space. We are currently dealing with the space alone. If this logic is adhered to, then in that case, based on the earlier Taylor series usage, what I can do is I can write, remember the equation. Okay, let me write it here. I had written f double dash x is equal to f of x plus h plus f of x minus h minus 2f of x divided by h square. What was h? H is the distance between the node. In our case, let me call it, delta x. Delta x. Let me call it delta x. So how will this equation change? This equation will change. We have d2t by dx square. And how am I going to approximate it? I'm going to write ti plus 1 plus ti minus 1 minus 2ti divided by delta x square. And that is how you can easily now, even by using an Excel sheet, solve this problem. You don't even have to write a Python code. By simply using an Excel sheet, you can solve this. What should be the next step? The next step would be to write down, the individual equations. What are those individual equations? Very simple. First thing is that we'll write the equation for TB1. No, we cannot do that. Why? There are no boundaries, or there are no nodes on the left. There are no nodes on the right. We can create a ghost boundary cell, but that discussion is for some other video. For now, we cannot do that. What then? What do we do? We'll start with T1, the unknown. So I will write T1 is equal to TB1. TB1. What next? Plus T2 minus 2T1 divided by can I write T1 here? Yes, if you thought about it, you are right. No, what should I write there? 0. Why? d2t by dx square was 0. Hence, I will write 0 here. So 0 is equal to TB1 plus T2 minus 2T1 divided by delta x square. Now I can quickly notice this is anyway going to go away. So I may very well avoid writing it for now. And remember this applies only to the present case. And if I rearrange everything, the unknown, T1 is my focus right now. So T1, I can write it as TB1 plus T2 divided by 2. And if this is going to be the case, I can write the same equation for all the other nodes T2 to T5. And if that is going to be the case, how many equations do I get? How many equations do I get? I get 5 equations. How many unknowns do I have? I have 5 unknowns. What about TB1 and TB2? We know their values, so they are not unknown. So we have 5 equations. We have 5 unknowns. We can easily solve this by using simultaneous equations or elimination method, matrix, whatever suits you. You can easily find the solution. And spoiler alert, the solution is going to be a simple straight line linear distribution, because notice we are simply taking the average of the neighboring nodes. It's a simple straight linear distribution, and that is how you complete the solution step. And in post processing, you simply plot the contour. In this case, it's a simple straight line. Let us now solve 2D steady-state diffusion. Again, let us follow all the steps. The first step would be problem definition. Now in this case, the problem is that we have a square plate. Inside, we have a heat source. Right? We have a heat source which is at, say, a constant temperature of 100 again, and all the other boundaries are at 30. So 30 degrees Celsius, 30 degrees Celsius, 30 degrees Celsius, and 30 degrees Celsius. And we are now supposed to model the conduction. Obviously, the heat is going to spread out. Now we have to model that. We have to solve that problem. First step, problem definition. I have defined the problem. The domain has been generated. The material properties, again, we can assume it to be uniform. All right. In that case, what should we do? The next step would be, okay, what is the governing equation? The governing equation would be this. Because we have 2 dimensions, we'll have to move from OD to PD. Temperature is now going to be a function of x and y, unlike before, hence we'll rely on partial differential equation. One thing is missing. In the earlier case, the diffusion coefficient, we skipped it. In this case, we cannot, because there are 2 terms, right? So we'll have to consider it, right? So I will write the diffusion coefficient which is outside as maybe alpha, and here also alpha. So maybe alpha x, alpha y, if they are different in both the directions. Again, if they are same, again it will come out as a constant and go and join 0. So again, in this case, since it's a steady state equation, fortunately we skip that part, because we are assuming it to be uniform in all the directions, homogeneous material properties. So that gives us the liberty to do so. So this is our governing equation. What is the next step? We have drawn the domain. Let us draw the geometry. The geometry is this. Simple rectangle. End of story. We'll generate the mesh. In this case, we will have a 2-dimensional mesh. And how will that look like? Simply, we will have an array in both the dimensions. Simple. So we'll have nodes spread out the entire domain. Simple. A nice rangoli, if you may. Now, having done that, let us draw a template. Now, in the earlier case, we had taken a simple template in 1-dimensional. Now, we will do that in both the dimensions. So, this will no longer be Ti, but Ti, j. Here, we would have Ti, j, say +1, Ti, j, -1, Ti +1, j, and Ti -1, j. So we will adopt this stencil to convert this and this, both these differential operators or other terms, to algebraic form. Okay, so what we have done is we have defined the domain, we have defined the problem, we have defined the the boundary conditions also we have defined. The initial condition, initially I will assume everywhere 0, gradually we'll update it. Then what else? Or I may assume initially 30 everywhere and then I may update it. Let us then convert it. Convert these individual terms to algebraic form. So let me clear this out. Now, so let us look at the individual terms. Dou 2t upon dou x square. How will I represent that? I will represent that as ti plus 1 comma j plus ti minus 1 comma j minus 2 ti comma j divided by delta x square. What about the other term? We have dou 2t upon dou I square. How do I represent it? I will write ti comma j plus 1 plus ti comma j minus 1 minus 2tij, and we'll have delta y square. Simple. And what is our equation? The equation is dou 2t upon dou x square plus dou 2t upon dou y square is equal to 0. So we'll substitute it. These values over here. What do we get? I'll simplify and write it because eventually that is what is going to happen. So we'll write ti plus 1 comma j plus ti minus 1 comma j plus ti j plus 1 and plus ti j minus 1 minus 4 ti comma j is equal to 0. Now what are the things that I assumed here? Delta x is equal to delta y. What does that mean? It means a uniform structured mesh. So all the nodes are equidistant from one another. We can make that assumption, yes. And if we do that, this is what eventually we'll get. What does this mean? It means, and if we rearrange the terms, you see now, I'll throw this on the other side. So we'll have 4 ti comma j, and if I divide or take it this 4 down here, so we'll have 4 here. Voila. What does that mean? It means we are simply going to take the average of all the neighboring nodes to calculate or update the internal value. And now this is going to be your discretization equation. Simple. Now suppose now you decide to write a code. How do you write a code? You write the code exactly by following all the steps that we have discussed. You will define the constants, and then you will give the boundary condition, you will give the initial condition. In the main loop, you will add this discretization equation. And in post-processing, matplotlib, if you're using the Python library, you can use matplotlib library for plotting, and you are done. You're good to go. It's that simple. Now, let us talk about unsteady case. The one-dimensional and two-dimensional steady-state cases were very easy to understand. So let us look at, one-dimensional unsteady conduction. What would be the governing equation? Dou t by dou t is equal to alpha dou to t upon dou x square. No zero. Now we have the time term on the other hand. So we have discussed how to discretize the space. Now we need to understand how to handle the time term. And this is where the different schemes come into the place. So we'll talk about it. I will adopt a very simple approach in explaining this. You will find different explanations in different books. I will adopt a very simple explanation from where you can start. That would be not the end. You can read Professor Suhas Padankar's book for more details. I'll give you a very simple case. Now, let us repeat all the steps. Let us define the problem. The problem here would be the same as the steady state case. We will have a domain. We will discretize it into nodes. We will have the first boundary. Let us call it maybe 100 degrees Celsius. Here 30 degrees Celsius. Initially everywhere maybe we have 30 degrees Celsius. Say we have taken only 4 nodes. We are now supposed to find the value of these nodes. All right. How do we do this? So if we take or if we consider one-dimensional unsteady conduction and say we have taken some nodes inside, we have defined the problem. Again, the material properties are uniform. We have the governing equation. Boundary conditions we have defined. Initial conditions we have defined. Now let us use the finite difference, the discretization, the Taylor series discretization approach that we had discussed earlier. Let us use that to handle this term. This we already know. What about this? Separately, if we want to represent this, how we are going to write it? Very simple. And remember our stencil. We had Ti, we have Ti plus 1, Ti minus 1. If you remember, f dash x is equal to, we had written as f of x plus h minus f of x minus h divided by 2h. Now, if you think of applying this for time, I mean, that is how generally, you may think as a new, user of CFD or someone who is very new to this concept. You may think that, okay, why not I, apply this directly and I write something like Ti plus 1, Ti minus 1. No, that is for space. Remember, do not get confused. Because in space, we have left, right, top, bottom, front, back. But in time, and sadly that is the case, it's a one-way coordinate. So time is a forward marching, operator. It is only going to increment. We cannot, take the past and future to calculate the present. No, the future is not known. So we'll have to rely on the past to calculate the present value. Or if you want to look at the other way, use the present value to calculate the future. Let me put it that way because that would make more sense to you. So Ti dash, I'll call it the new value. And Ti would be the present value, and this will become delta T. So this is not the right equation for this. What would be the right equation? What would be, the right equation? Let us look at it. If you remember the forward Taylor series that we had written earlier, what had we written? Or what did we write back then? So we had written this. Let us assume everything as the higher order term and ignore it for now. So I can rearrange these three terms and I can write something like this. And this perfectly fits this case, because here the future is calculated based on the present, right? And h would be delta t, right? So this is how we are going to convert the first order differential term in terms of algebraic equation. So let me write it again. So we have dou t upon dou t is equal to ti but dash minus ti divided by delta t. This represents the new time. And dou 2t upon dou x square, we know that already. Ti plus 1 minus plus ti minus 1 minus 2ti divided by what? Delta x square. Simple. Now let me put it together. I will write ti dash minus ti depending or divided by delta t is equal to ti plus 1 plus ti minus 1 minus 2ti divided by delta x square. And now we'll have to rearrange this. And we have to rearrange such that we have all the unknowns on the one side and knowns on the other. If we do that, if we rearrange such that all the unknowns are on one side, all the knowns are on the other side, right? This would be known as the explicit form. And if we rearrange it such that all the knowns are on one side, which will be calculated based on iterations, or let me put it another way, the present values. Suppose, okay, let me put it other way. Now in this equation, to avoid confusion, in this equation, what is not known? The present value, the future value. The future value is not known, which is ti dash. So if I rearrange all the terms and put ti dash alone on the left side and everything else on the right side and calculate ti dash based on the other values, that approach would be known as explicit approach. Right? And if I rearrange or all the terms, keeping them everything like together, and use ti dash to calculate ti plus 1, ti minus 1 through iterations, that approach would be known as the implicit approach. And there would be one more approach, which is the Crank-Nicolson approach or Crank-Nicolson model, wherein what you do is like you take 0.5 of the past, 0.5 of the present, or 0.5 of the future, 0.5 of the present, and like you calculate the future. So that is like a mixed approach, Crank-Nicolson, and then there are so many models. One can suggest. So what I'm trying to say is, there are different ways to handle this equation, but the most simple or the simplest would be to rearrange everything and keep the unknown on one side. Right? So let me do it here. So if I rearrange everything, see, I write it this way. Plus ti plus 1 plus ti minus 1 minus 2ti divided by delta x square. So in general, and this is a very new, this is a very nice way to look at it as a new user would be new value. This is very nicely given in Professor Stephen Chapra's book. Old value plus delta t into slope, and you can arrange in this fashion. So this is the explicit fashion where the unknown is on one side, all the known on the other, and we will calculate. Obviously, these are also not known. We are assuming, but at least we have some value for it, and then through iterations we can correct them. Now, even by using an Excel sheet, you can solve this. What you have to do is simply in one column enter this, leave room for this. In the other column, enter all these values, calculate this, and for the new iteration, update the TI value and all the other values. So that is how you can easily calculate this. All right. And this is how we'll update it. So for instance, let me give you a very simple example, which I did not give in the steady state case on purpose because that was a simple matrix case. But let us look at this case. So what I do, Ti dash and Ti plus 1, Ti minus 1. Right? Suppose I have these values and I have to calculate for maybe T1 and then T2, T3, T4. So I'll have to do this exercise, multiple times. So in Excel or even while writing the code, my idea or my attention would be solely focused on updating these 4 temperature values. How can I do that? So I'll write it here. So I have one boundary 100, the other is T1, T2, T3, and maybe T4. And here I have 30. So I'll give you or show you maybe 1 or 2 iterations. So that is how you will be able to easily understand how to go around this, right? So maybe all right. Now, so okay, let us maybe change the boundary conditions a bit so that we are able to appreciate this particular thing. So for simplification, what we can do is simply make this 100. Obviously, after some time, everything will become 100. So, but that process we can, I'll be easily able to write it here and explain it to you. So as I said, there are 4 nodes and both the boundaries are 100. Suddenly they are made 100. Okay. So now I have defined the problem, domain, mesh, everything is done. We'll have to start. But there is one thing missing, one thing extra. if we have delta x, we had delta x before, now we have delta t. Now delta x here is a very straightforward thing to calculate. There are like 1, 2, 3, 4, 5 pieces, and we assume 1 meter rod, so we have delta x is equal to 0.2. So this is very straightforward. What about delta t? How do you decide the value of delta t? So here, it is a question of stability, because if you use a very high value of delta t, your simulation is going to diverge. And if you use very less or very small value of delta t, the simulation is not going to diverge, but it will take eternity to reach to the final solution. So we have to again, play around a little bit. So it is led to, guesswork. And also alpha is there. So we'll have to also decide the value of alpha. So say assume we take the alpha of 10 raised to minus 4, the value of 10 raised to minus 4, and for this delta t, say we may rely on or deciding the value or the expression for the calculation of delta t. Maybe the idea we can use is that delta t should be less than or equal to delta x square divided by alpha for stability, right? So what does that mean? So if we calculate that, right, it's coming out to be something like 312.5 seconds in this case. If we just substitute and everything, I did it very quickly now in my calculator over here, and so we can choose delta as maybe 300 seconds. And you can check. So if we say calculate the Fourier's number, right? So Fourier's number alpha delta t by delta x square turns out to be 0.48, which is less than 0.5. So it is a very nice number for the sake of stability. All right. So if we look into this, it's a fairly easy thing to do, right? And again, the approach that I have used, because of that I have gotten this value of delta t. Not every time it may work. You have to keep that in mind. And depending on the situation, depending on the stability, again this formula is not universal. The formula is going to change. So you'll have to be very mindful when you operate. So you'll have to check which problem we are solving and what stability formula we should apply, and depending on that you should calculate the value of delta t. Obviously you can always use the guesswork, but that will unnecessarily prolong your simulation. So that doesn't make any sense. All right. So if I apply this logic, I eventually end up getting the discretization equation Ti dash is equal to Ti plus 0.48 Ti plus 1 minus T plus Ti minus 1 and minus 2Ti. This is what we get. So if I use this equation and I update the values, I'll show you a few iterations. So at the time 0, the values would be 100, 0, 0, 0 and 100. And at the next time, which is 300 seconds, and this seconds is not the real life seconds, don't get confused. This is computational time, a different paradigm. Okay. So 100 remains 100. The boundary conditions never change. They stay what they are. This becomes 48. This becomes 0. This becomes 48. How did I calculate these values? Not magic though. I used simply this. These three values for calculating this value. You can check yourself. So what do we have? 100, 0 and 0. So 100 into 0.48, which is 48. And what is Ti? 0. So 0 plus 48, 48, beautiful. And what about this? 0, 0, 0, everything is 0, so this stays 0. What about this? Again 48. Why? Because there's 100 over here. And what happens at the next time step? 100 stays 100, 100 stays 100. What about this? So this time now we are going to use these three values for calculating this. I have pre-calculated this. It turns out to be 71.04. This turns out to be 23.04 and 71.04. Now notice how this value got updated. And similarly now, these three values will keep on updating. And if you plot the graph, right? If you plot the graph, you will notice, for different temperature values, they will increase initially, and at some point, all three of them will achieve more or less a constant value. And, just for your information, you can run this simulation for eternity. Yes. So you'll have to stop the simulation on your own. In steady state simulations, the simulation usually stops when the convergence is achieved. You can put the condition. Here also you can put that condition. But if you don't put that condition, the simulation runs for eternity. Why? Because once the constant values are achieved, it goes on and on. Because they are never achieved. Very poetic. What does that mean? Now you notice how from 0 this jumped to 48. From 48 this jumped to 71.04. And from 71.04 they will jump to some values. And at some point they will be like 99.999999, and but still they will be updating here, maybe 1 or 2. So how do you decide? How do you decide when to stop? So what we do is usually we say that, okay, we'll up to a certain digit, we'll monitor the answers, we'll monitor the values, and when it stops changing, maybe up to 6 digit, 10 to the minus 6, values or the order, we will stop simulation. Until then, the simulation runs. This is how we define something which we call as convergence. And this is convergence criteria. The idea is very simple. You can run the simulation until eternity. At some point we have to stop. We cannot prematurely stop, because if suppose I decide, okay, I'm done, I'll stop the value, stop the simulation here, you will have all the wrong values. You'll have all the wrong values. If I suppose stop the simulation here, and if I stop the simulation here, I will have to check their differences. And if the difference is very less, then I may say okay. But then it is all left to ambiguity. So hence what we do, we establish clear criteria that if the values stop changing up to the last 6 digits, we stop the simulation. Or you may also put the condition that if the difference in values between the last iteration and this iteration does not change up to maybe 5 or 6 iterations, something like that. There are different approaches again there. So it's up to us. So this was how, or this was the two-dimensional, so this was one-dimensional unsteady conduction. Now let us look at two-dimensional unsteady conduction. What is going to change? You've guessed it. Time. Beautiful. What is going to change? The time. So the equation is going to be dou t by dou t is equal to alpha, and Now this time we will have dou to t upon dou x square plus dou to t upon dou y square. Beautiful. And how the discretization equation is going to change? Again, we'll have to write it in this fashion. New value is equal to old value plus delta t into slope. So here obviously we'll have ti comma j dash is equal to ti comma j plus delta t divided by, or let us not do that right now, we will have ti plus 1 comma j plus ti minus 1 comma j minus 2ti comma j divided by delta x square. Similarly, we will have plus ti comma j plus 1 plus ti comma j minus 1 minus 2ti comma j divided by delta y square. That's it. Hold on, let's stop right here. I have made a mistake. And no, I did not do it by mistake. The mistake was done on purpose. Why? I want to check whether you're paying attention. Now you tell me what mistake I have done. I mean, of course you cannot tell me. Comment what mistake I have done. What was our equation? Equation that we thought about considering is this, and I left out alpha. Did you notice? Our final equation, that the discretization equation, turned out to be something like this, that we had ti dash is equal to ti plus I wrote this. And I hope you noticed I missed out alpha. Right? So this also has to be considered, obviously. Why? Because it's right here. And unlike the previous case, here we don't have 0. We have an expression, and therefore alpha will stay. It will not go. And hence it will also appear here. And therefore this entire coefficient alpha delta t by delta x square will play a very crucial role in stability. Because you see, this plus this is the final answer for this. And whatever value comes here, if the quotient is either too high or too less, the simulation will progress accordingly, and hence we will take that into consideration. Now I hope you are able to point out this mistake. If you were able to, that means you are paying attention and you are able to appreciate the content that I am discussing. If not, clearly either you blacked out or I failed to grab your attention. In either case, please comment and let me know what's your thought, what did you notice or did you not notice, and accordingly let us move ahead. Keep an eye out for alpha. So if we talk about, say, one-dimensional steady state conduction along with convection, how does the equation change? Very simple. We will write dou, or rather u, into dou t by dou x, the convection term, is equal to alpha dou to t upon dou x square. Now, this we know how to handle. This we know how to handle. This is new. This is new. What is this? This is simply the velocity of the flow. For now, in this equation, it will be a constant. So nothing to worry about. So if I have to write the discretization equation, u into ti plus 1 minus ti divided by delta x is equal to the same as before. We will write ti plus 1, right, plus ti minus 1 minus 2 ti divided by delta x square. That's it. Now you can rearrange the terms, right? You can rearrange the terms and you can get to the simplified equation. What will happen, a crazy thought, what will happen if I make it unsteady? So we'll have a new term which is tau t by tau t. And how do you handle that? We already know it. You already know it. How do you handle that? Here, one more term will come. Or another term will appear. What is that term? We have ti dash minus ti divided by delta t. Obviously that plus this entire thing. And if we are talking about the second dimension, 2D, how does this equation change? How does this equation change? Think about it. Think about it. So we write tau t upon tau t plus u into tau t upon tau x plus v into tau t upon tau y is equal to alpha tau 2 t upon tau x square plus tau 2 t upon tau y square. It's that simple. What are these u and v? Simply, u and v are the velocity in x and y direction. Again, constants. Nothing to be worried about there. This, by the way, this equation that we are looking at will act as the energy equation in a two-dimensional fluid flow case, meaning along with the Navier-Stokes equation or along with the momentum equation of the Navier-Stokes equation, this will act as the energy equation for an incompressible two-dimensional flow. And you see how we have made this journey. We started with computational fluid dynamics introduction, or in fact, we started talking about the various ways to solve a problem. We talked about the numerical method, then we talked about the computational fluid dynamics, then we talked about discretization, then we talked about finite difference method, and now you have arrived at the energy equation. Energy equation. Beautiful. And all this we have done by using finite difference method. Now this, of course, you cannot solve with Excel. Don't code yourself. You'll have to write a code. That would be the most efficient way. This code, software, what to do, what not to do, all these things for future. In this video, I wanted to talk about all these things. I hope I was able to explain, properly. To sum it up, this was your first video in the world of CFD, I'm assuming, or your introduction to the world of CFD through finite difference method. We have seen theoretically how to solve one-dimensional, two-dimensional, steady-state, unsteady-state, conduction, convection problems. I hope, again, I was able to explain properly, and we will meet again in the next part where I will talk about finite volume method. And there will be videos, separate videos on coding as well. So thank you. Have a nice day.